Good afternoon. This is the RBE550 motion playing presentation. My name is Colton Lehue, and I'm here with Edward Jackson and Aaron Erickson. So to kind of a brief from our last project proposal, we had some changes from then until now. So one of the biggest changes was reducing the amount of objects that we were grabbing in our simulation. So initially we were looking at a subset of items, and we moved to looking at one item and focusing on navigating that item through a doorway to avoid collision. This big change came from reducing the focus on computer vision and increasing that focus towards the motion planning. Next slide.
So with this new change in mind, our overall workflow looks by trying to create a point cloud of what our arm sees through the end effector. Then we segment what we see so that way we only care about the object. We don't really care about the floor or really the obstacle itself, such as the doorway which you see in the bottom. From that segmented view, we calculate the centroid, and then now with the centroid, we are now able to move our arm to the centroid, grasp, and then place it to a location that which we chose to be behind the board. And we look at this image, we see the orange path is actually where we want to follow, and our main obstacle is going to be this red region.
Going into a little more detail on the workflow of how we're going to achieve this operation, we actually start in the grasp not found position, and the robot immediately starts repositioning the camera to try to find an object. Once it finds the object, it parses the raw point cloud data input and filters it using the segmentation method, and then extracts the 3D centroids. Those centroids are fed to a grasp selector, and if the grasp is possible, the object is grasped, lifted, and placed. Next slide. A little more detail on the point cloud piece of the workflow. We use the PLC library to do a lot of the point cloud processing. One of the main algorithms we're using is the planar segmentation algorithm. This is a ransack algorithm that just determines what points support a plane and occludes them from the results. The centroids themselves are just a simple average of the filtered point cloud, and then a KD tree and a nearest neighbor search is performed in order to select a point on the surface of the object and then calculate the normal. One of the main problems we had with the normal selection is that the orientation is arbitrary, so you have to select a explicit viewpoint in order to set the orientation of the normals. You can see on the picture here the difference between a planar segmentation model and a filtered model. And in the filtered model, our cube is very obvious and the centroid is trivial to calculate. Next slide.
So for some of how we handle robot kinematics is we utilize MoveIt, a motion library that utilizes the open motion library planner to plan and execute trajectories. We also paired MoveIt with a server client setup, so that way we'd be able to command the joints and gripper through our commands. So now we have a way of utilizing our robot through code through MoveIt. MoveIt is also really advanced in that it can consider collision variables in the environment, and we utilize this fact to be able to detect the door frame, so that way we do not hit it when trying to place our wooden cube from point A to point B. Finally, our object properties. We assume that the centroid is going to be used as a target post for the initial grasping, and we also want the object to have a low mass and small inertial properties, so that way the arm really isn't going to be picking up anything too heavy, and we won't have any weird effects that we aren't expecting. So this process looks as it scans the floor, finds the centroid. It's going to pick it up just a little bit, so that way it doesn't drag the object along the floor, and then it's going to do an RRT algorithm through the door, and this is what MoveIt utilizes.
So for our simulation environment, we used a variety of common applications. So for starters, our operating system was 220.04. The framework we were using was the ROS1 Noetic framework, and for simulations, we're using Gazebo. The major nodes that we had in ROS were the Panda Sim, which covered the basic simulation of our robot, the MoveIt client and server, which Edward had said this kind of working in tandem to push the poses to our simulation, and lastly, the TCL processing. This is responsible for dissecting the point clouds that we had. So for planning, planning was performed using the OpenMotion planning library, OMPL within MoveIt. We utilized an RRT Connect algorithm. So this is a basic bidirectional RRT path planner. Like you can see in the diagram below, this is utilizing two trees, one at the start position and one at the goal position to achieve your overall path. We also had a hybrid explicit grasp. We discussed a little bit how we had some issues with gazebo dynamics, and this is a way to kind of compensate for those dynamics.
So for some of the challenges and obstacles that we faced, including the grasping dynamics not being super accurate, Gazebo is not well known for its accuracy, and the grasping often would kind of stick and maybe fall, maybe not. It really was arbitrary depending on if something was chosen or something was not. We also have the dynamics are kind of unrealistic. When we were utilizing more advanced objects such as a mustard bottle, what would happen is it actually falls down and back up and falls down and back up again. Obviously, this breaks the law of thermodynamics because that can't possibly happen forever. We also know that MoveIt without a lot of help, the movement through MoveIt is not optimal. It will kind of take really arbitrary and strange paths to go from point A to B sometimes, unless it is really well conditioned.
So one of the main filters we used for the point cloud filtering was the planar segmentation filter. And the best part about this algorithm is that it filters planes, but it also poses some issues with some planar objects. If an object was considered too planar, it would occlude it from the results. So we ended up having to pick a large enough plane to occlude so that our smaller planar cube wouldn't get occluded from our results and could be picked up.
In the beginning of this project, we discussed using a convolutional neural network to aid with object classification for our optimal graphs. This was removed as we entered the final push in order to kind of shift the focus towards motion planning and less on the computer vision side of things. And lastly, the grip scoring function was not completed. So as we talked about the kind of difficulties we've seen with grasping in general with Gazebo, in order to kind of achieve experiments to see which would give us the best grasp, it was kind of difficult to do the dynamics that are. So no grip score was calculated for the project.
So we're happy to show some of our results in demonstration. On the left, we can see our arm moving, detecting that centroid, and moving to go grasp it. We can see here, grasp. It moves up, as we talked about, to try to compensate for those gazebo dynamics. And then, avoiding the door, it moves through and places the object. Now on the right, we have a bit more. We see the point cloud, this white piece, and Aaron will talk about it a bit more.
Yeah, so you can see at the start of the simulation here, that's when the object is first detected and the floor is filtered out. Once the object's detected, the point cloud data is no longer relevant, and it knows where the object is, it goes and grabs it, and then executes the rest of the planning algorithm. And then finally, just our project timeline, how everything wrapped up. We hit most of our goals. The only tasks that we didn't quite finish were the scoring function for the picking up and placing of objects. But all our other metrics we hit, and all in all, I think a very good project, and I learned a lot. Thank you.